Good afternoon to everyone. Okay, we were talking about time domain OCT, right? And in case of time domain OCT, as it is explained that as the reference mirror over here moves, right, and when the path length difference between this reference arm and this, let us say, sample arm is within the coherence length limit, okay, within that we will see the burst of such interfering, right, patterns we will see. Now, this burst is basically due to the interference at that point of time, and subsequently that burst will disappear if the path length difference is more than the coherence length, because as we also observed that now the phase mismatch between all the waves which are being reflected will result in an amplitude outcome which is more or less and some average outcome. Okay. And let us say, so based on this, in time domain corresponding to each burst we will be able to find out different positions of this, and this reflection interference free this burst is seen whenever there is a reflection. Okay. Reflection is due to the refractive index change in the material. So, if the material has some type of inhomogeneity along the layers, we will be able to observe those inhomogeneity, okay, in terms of this. However, in case of time domain OCT, we will have to move the reference mirror by a certain distance, we will have to move, keep scanning, and So, if we want to cover let us say we want to, so this is, let us say, it is an object and we want to scan this object for to achieve 3-dimensional information about this object. So, when the light is incident on this at this position, then we will get depth information. To what extent, what is the depth information that we can achieve depends upon how the reference mirror is moving. To that depth, some information we can achieve to certain depth. Of course, there will be a limitation, because as the light penetrates through the substance, through the sample, due to scattering, due to some absorption by some molecules, etc., there is some extinction, So, the reflected signal reflected back will keep diminishing. Okay. So, that will decide the depth of penetration, that scattering, etc. But till that point, we will be able to see till the intensity of the light is sufficient enough, more than the noise equivalent power of the detector, we will be able to see that as the signal. And so, this position where we get the depth scan, okay, this depth scan is known as A scan, will give you one position. Now, if I want to cover the whole object, we will have to laterally move this source or the object sample or the source has to be moved laterally, so as to cover this lateral direction view. So, that is basically it will end up with a B scan. Okay. So, A scan is at one position, you achieve the depth information, and when you start moving either the object or a sample or the light irradiating light source at different positions laterally, you will be able to achieve B scan. Okay. So, that is will give you B scan. Okay. Is it okay? And then in order to cover the whole width in this direction as well, in the depth direction, we will be right scanning the laser beam like this, is not it, right. So, you will be able to cover the whole right object, of course, but if you can recall that for all this, each and every A scan, we will have to have reference mirror to move, right. So, if it is a mechanical movement in terms of reference mirror, it becomes right quite tedious, it will consume time. So, reference mirror movement is either mechanical, okay, using right a micro stepping motor, etc., but it is tedious, one approach. Another approach is we can use piezo electric transducer approach, so that when we apply certain voltage to that piezoelectric material, the material will accordingly change its dimension, right, laterally, and according to that the reference mirror position can change. Okay. So, but it has a limited depth. So, in order to expand its large movement, let us say few hundreds of micrometer movement, we may need a stack of such piezoelectric transducers or some mechanism to convert that position into right lengthwise large displacement, magnification, etc., possible. So, using some ideas. So, that is a mechanical movement, piezoelectric movement. There is another approach which is electro-optic approach, okay, electro-optic approach. Now, in this case, in the case of mechanical movement, mirror is physically moving, right. In piezoelectric movement also, mirror is physically moving, right, front and back, depending upon the piezoelectric displacement which can be achieved. The mirror which is the reference mirror will move as the piezoelectric material dimensions accordingly alters. The piezoelectric mirror attached with that piezoelectric the mirror attached with that piezoelectric, right, mechanism will move. However, in electro-optic mechanism, what is done is we change the optical path length, okay, we change the optical path length not by physically moving the reference mirror, okay, right. L is not altered, but the path length is altered by introducing refractive index change, right, because optical path length is n into L, right, difference in reference mirror sample mirror, right. We know, if you can recall Michelson interferometer, the optical path length, right, depends upon. So, if this is the light source, right, this is a reference mirror, let us say this is a sample arm, and right reflects back, we will observe, right, using detector the outcome, which this detector outcome will depend upon the phase difference, which is correct, this is one. So, if I introduce electro-optic crystal, an electro-optic crystal whose refractive index can be altered over here, okay, then automatically the optical path length will change, is not it, the path difference will appear. Now, this N can be altered electro-optic crystal. There are certain birefringent crystals, okay, right, certain type such as lithium niobate, okay, or potassium titanyl phosphate, or right, KTN, potassium titanyl nitrate, etc., KTP, etc. These crystals, when you apply electrical field in one particular direction, okay, if you apply an electrical field across this, then the refractive index of this material accordingly taken care, it changes, okay, and it indirectly introduces the optical path length difference, okay. So, this is there is no movement of the crystal, no mechanical movement, it is right, no mechanical movement, still it can achieve the optical path length difference, okay. However, the limitations may be the how many, right, millimeters, that the distance it can allow, right, optical path length difference it can allow may be limited, but still it is possible. It is very fast, much faster than the mechanical, right, movement. It can work with few megahertz, right, or kilohertz frequency, modulating frequency. So, you can imagine that every, right, within, right, let us say if it is modulating with few kilohertz, right, within millisecond order, okay, the A scan will be done, or within microsecond order A scan can be done, and then it will continue swapping, right, laterally, and acquiring B information. So, few seconds the whole object can be scanned, okay. So, speed depends upon the speed of scanning depends upon such, right, parameters to control, okay, electro-optic approach or mechanical, etc. Now, coming to approach wherein can we acquire similar information with the help of right, frequency domain approach, okay, slightly different from this, but before this, okay, maybe, okay, that is just to give you, right. So, we, right, this is, so this is what I was right, now you are, it is clear to you that it is possible, and the parameters which controls this, as I told you, when we are using it for ophthalmology applications, we need depth of lateral resolution, delta x can be decided, right. The confocal parameter also gives us information about depth of focus, as well as the theta scanning angle, right, which is possible within this will give you the basically the lateral field of view, okay, field of view for this ophthalmic. And as I told you, using this combinations we will be able to scan this whole retinal surface, right, easily, and acquire the information about the right, layer by layer information of this retina, which we will see it in the subsequent afterward slides. Similarly, for skin also it is possible, right. So, you can use A scan or 1D scan will give us the depth information about this skin depth, where the light penetrates and provides different layers, right, based on the refractive index. These are all false colors which are based on the refractive index change, right. The each reflection points are here, right, within this scan, and then 2D scan, right, lateral transverse scan will give us the B, and then the 3D scan, right, zigzag scan will give us the complete information about the skin which we are trying to acquire. Now, this information is basically useful for dermatology, right, applications, etc. And what we have to decide about the wavelength of the light, what we use here, right, in such cases. So, that is decided based on the absorption, right, melanin absorption, blood as well as water, right. All these constituents over here will affect the depth of the basically the biological window, and the region between 800 and 1000 nanometer, right, 1200 or 1300 nanometer is a biological window as far as we consider the OCT applications for various human, right, this either skin or retinal imaging or tooth dental imaging or even right endoscopy using OCT and coupled with endoscopy, we will be able to observe up to the depth of few millimeters or right millimeter order using the wavelengths of the right with 800 nanometer to 1300 nanometer. This window is used basically. Okay. So, now we come back to right OCT, which is just now whatever we discussed was time domain OCT, right, where we try to move the scanning or the reference mirror and achieve the depth information from different layers of this samples. Okay. So, depending upon layer 1, layer 2, layer 3, we will obtain right 3 this peaks, and that can help us to determine the optical right path length of these layers, etc. Distinguish these layers, we are distinguishing it based on the reflection coming back from this, correct, based on the refractive index change. Now, there is the question is to avoid such scanning, right, mechanical scanning, etc., can we use some other approach? The other approach is based on the Fourier domain OCT. So, in this case from each layer, okay, in this case let us say it is also Michelson interferometry. From each layer we are receiving signal back for each wavelengths. Let us say laser the light source has a broadband width, right, broadband width, and corresponding to each of these wavelengths, right, we are receiving the reflections from each of these layers at a time simultaneously, all of this. If we achieve, then the if we see this information, observe this information using a spectrometer. Okay. So, what spectrometer does is each of this reflected light intensity, right, is being captured using a spectrometer, where spectrometer is nothing but let us say optical grating and a CCD detector array or CMOS detector array will capture wavelength wise information. Okay. Grating will diffract the light, depending upon wavelength the diffraction angle will be different, and the detector array will right according to its right position will be able to give us outcome corresponding to different wavelengths. Okay. So, red may be here, yeah, orange, yellow, green, right, etc. Of course, we may not need such a broad right wavelength, it may be 100 nanometer range. Okay. So, 100 nanometer range, this wavelength will get accordingly right resolved on this detector. So, now what detector is doing is capturing for each wavelength, capturing the information for this, right. Now, when lambda 1 reflects back from surface 1, surface 2, surface 3, they will all add up, right. Now, depending upon the phase, lambda 1 is reflecting from surface 1, it may have phase phi 1. The lambda 1 is reflecting from surface 2, it may have phase phi 2, and lambda 1 reflecting from surface 3 will have phase phi 3. But when they add up electrical field, depending upon their phase, the overall intensity, right, or the electrical field amplitude will get decided. Now, so the signal what we will see from the spectrometer is a complete right information about for each wavelength each let us say this is written in terms of frequency over here x axis. If it is in terms of wavelength, for each wavelength what is the intensity amplitude, right, intensity, we will be able to capture. The spectrograph will provide us information related to each of this, right, frequency or wavelength parameter. Now, frequency is of course proportional to 1 by 1 by lambda, correct. So, and we know wave constant, propagation constant, right, is also 2 pi, right, by in vacuum it is 2 pi by lambda, right. So, lambda. So, basically this spectrograph spectral output is indirectly represents the bandwidth, right. Depending upon the light source we will get another spectral, but now the intensity of that spectra depends upon the sample configuration, is not it, right. Input light source is broadband like this, the output light source will also be broadband similar to this, but output means detected with this detector spectrometer, but only thing is the intensity variation at different wavelengths will depend upon constructive, destructive, whatever may be the interference which each wavelength is experiencing from different layers. Okay. And if we apply a Fourier transform, right, basically to this, we will be able to capture the depth information, Z information. Okay. So, that is basically shown over here. So, for FD-OCT, okay, so for FD-OCT, so frequency domain, okay, FD stands for, TD stands for time domain, FD stands for frequency domain. Here at a time, without moving the mirror, we are capturing the whole spectral information, right. And this spectral information is right, is basically has data, hidden data about each of this, right, peaks of this, right, of the sample refractive index change. So, the spectrograph which we obtained corresponding to the wave constant is proportional to Sk, which is a spectrally resolved, right, spectral for each of this propagation constant lambda 1, lambda 2, lambda 3, correspondingly 2 pi by lambda 1, 2 pi by lambda 2, k 1, k 2, k 3, and for each layer, okay, each layer, if there are n number of layers the sample has, there is a corresponding reflection from the reference mirror, from the sample mirror, right, each layer, right, sample, and cosine of 2 k Z n, okay, right. So, basically this whole information is spectrally resolved and it contains, right, containing signal component, the whole okay. Whole depth till it propagates, right, and it will be able to. I will also show you that there is one more limiting factor which will decide the depth information that we can achieve with FD-OCT. Okay. In time domain OCT, the depth information depends upon the intensity of the reflected signal. As it passes through due to scattering, due to absorption, etc., the reflected signal intensity may starts decreasing, and detector noise and the signal strength will decide, okay, the signal right outcome. But in case of FDOCT, of course, this depth information is controlled, is also affected by this scattering as well as this absorption, etc. Over and above, right, it also gets affected by one more parameter that we will see it in the last. A scan, if we apply fast Fourier transform and or inverse Fourier transform and obtained the depth information, basically depth information, okay, information, okay, from the spectral scan, okay. What we have is the data based on FDOCT, the intensity from the spectrometer, okay, spectral intensity, right, spectral, right, corresponding to propagation constant or frequency or wavelength, some information we have, right, and this spectra depends upon each wavelength, right, which is reflected back, how they are constructive or destructively interfering, right, from based on their information from each layer, isn't it, right, layer 1, layer 2, layer 3, all lambda 1 will come, but they may have different phase, how they constructively destructively interfere will provide that particular intensity. Like that we have all this, if we apply FFT to this, we will end up with right, the information which is a detector is going to now, right, provide is n equal to 1 to n r as reference mirror r from each layer into gamma 2 z n plus gamma minus 2 z n, okay. So, this will provide you the information. So, there will be mirror right image associated with it, and that indirectly is, okay, it is basically we will get this information, okay, that information. So, now this is the central component is a DC component, okay, from where the reference some particular reference position, wherever the two mirrors reference and sample arm, where they are based on that there is some delta z associated, that is here 0, and from there the depth information for each layer is captured, and see that information will be having a mirror image, because even if the sample would have moved this way, or if the reference mirror would have moved opposite way also, it might have also reflected, isn't it, mathematically it will have the mirror image, okay. I hope that you understand, right, right, either the mirror moves this way or sample arm moves this way, both way it can have, right, information. So, either the information can be in the plus z direction or can be in the minus z direction. So, that same such, right, peaks will be observed corresponding to this, okay. We will of course use it only one, right, real this part in order to capture the right, obtain the information z1, z2, z3. The advantage with the time domain, as I told you, is you need only one scan, okay, right, and that too no need of directing to even move its CCD array or CMOS photo detector array, line array can give you this information very easily, okay. Only thing is you need a computation in order to derive this information, okay. Secondly, the depth information, right, may be limited, okay. So, the depth information, just before we close, if I can give you that idea, that will, right, give you what it means. See, axial imaging depth, okay, that you can achieve. See, as let us say as we go and try to derive the information based on the optical depth that light can travel, okay, assuming that there is no scattering and no absorption. Okay. So, light can travel right at as much as possible, and every position, only problem is now the reflection, layer by layer reflection will decrease the intensity, otherwise it can travel. Now, each layer information is reflected back, right. However, as the depth, let us say if the surface from where this reflection is there is at 50 micrometer, right, depth, you will see the spectra like this, okay, with the distance between these two, maximum frequency of the decodes the maximum depth. The z depth of the signal is encoded in this right part. Okay. So, each of this will decide this z depending upon the depth, right, it is coming from. Okay. Now, if this surface is at 300 micrometer, we will observe the spectra like this. Okay. Now, if the depth increases, what is happening? The spectral resolution should be better, more right, should be better and better. If my detector, which is going to detect the spectra, has a poor resolution, I may not be able to resolve the depth information, okay, from where the signal is coming. So, that is the, you can see a limitation as far as, right, this frequency domain OCT is, right, a concern. So, how to assume or how to estimate this, right, that quickly 1 or 2 minutes. So, basically the detector array, right, will decide detector array, the resolution of the detector array, right, will help us to determine from which what particular depth the information can be captured, at the most maximum depth that can be captured. So, if there are n number of pixels or number of, right, detector points, right, which are distinguishing each other, right, information. So, and if the spectrum is covered from lambda 1 to lambda 2 wavelength, so delta k, right, which is based on the spectrum lambda 1 to let us say lambda 2 FWHM, let us say, okay, lambda 1 to lambda 2. So, delta k we know which is equal to 2 pi delta lambda by lambda square, correct, because k is 2 pi by lambda, right, delta k will be minus sign, I am not right considering. Okay. So, now you see, if you go back to this, now you see that within this delta k, this, see, this is what is the spectrum which is captured by the spectrometer, and within this delta k width, you can see that number of such modulations are basically each detector will be able to resolve this. So, every cycle, this cycle, every this cycle, it has 2 points, no, maximum and minimum, right. As you depth increases, the width of the cycle decreases, but every cycle has max and minimum. So, basically the detector, right, number of modulations that detector is basically capable of detecting is n by 2, correct. If there are n number of pixels, it will be able to detect n by 2 such, right, each single corresponding to single right wave cycle. Okay. So, the number of modulations which are maximum number of modulations that can be observed, which is equal to n by 2, okay, n by 2, okay, n by 2, and so this n by 2 is equal to total width delta k divided by spacing of a single modulation. Okay. modulation. Okay. So, delta k is 2 pi delta lambda by lambda square, and spacing, this is nothing but each spacing is pi by z, okay, pi, right, because phase will accordingly, right, pi by z, that maximum that we can achieve. So, z max, the depth that we can achieve, maximum that depth of imaging that can be achieved with FDOCT will depend upon 1 by 4 lambda square by delta lambda into n, right, number of pixels, right. Detector will also play a role in terms of, in case of FD OCT, okay, or spectral domain OCT. There is one more revision in this approach, one more slight revision. What I explained to you, right, FD OCT over here, FD OCT. So, in case of time domain OCT, it is, right, movement, right, coming into movable reference mirror will decide this peaks. In case of spectral domain OCT, it is no scan, nothing, it is a CCD or a spectrometer will give you the spectra, and FFT will give you this outcome. Now, here a spectrometer is used. Instead of a spectrometer, I can swap the light source also and obtain the information. Lambda 1, lambda 2, lambda 3 I can swap. Accordingly, each lambda 1, lambda 2, lambda 3 detector will give me the information. Okay. I do not use spectrometer, I use tunable light source in that case. Is it okay? Lambda 1, lambda 2 tunable. So, I can use a tunable light source, and the resolution of each of this spectral width of this will determine the depth that it can obtain, imaging depth that can be obtained. Okay. So, using this we can obtain information about eye, information about retinal imaging, lens of the eye imaging, everything is possible, right, very easily, which is not possible by any other simple approaches. Okay. Depth scanning is not easy, right, that can be achieved. Secondly, we will be able to see through the skin surface to certain limit. Okay. We can see through the tooth surface to certain limit. We will try to see such examples, right, in terms of OCT with, right, this. So, right, so either either the source can be tunable or spectrometer is available in frequency or spectral domain OCT. In time domain, it is movable mirror which determines. Okay. So, this is the whole instrument, how it looks like. Okay. There are some modifications I will try to give with respect to the how we apply, use it, okay, for dental applications or for eye imaging modalities or for skin, the things may be slightly different, and the applications are enormous in terms of right, OCT, because it is a non ionizing source, it will not damage the tissue, right, it is only very right, power will be very much limited within the permissible limit of this. So, it will not damage the tissue and it can work very well. Okay. The limitation is the depth information that we can achieve. Okay. Thank you very much.